Michael Joyce. I've been with R&D Services for 13 years. R&D Services is an accredited third-party test lab and inspection agency. We're celebrating our 30th year of business this year, so been around for a while. And we specialize in thermal and physical properties of building materials. And that's a real fancy way of me saying that we measure insulation, and we specialize in insulation products, materials, and the evaluation of those materials. A little bit of a history of R&D Services. We were founded by Dr. Dave Yarborough and Ron Graves. So while this is our 30th year as a business, the history of R&D actually goes back to the energy crisis of the 70s. At that time, Dr. Yarborough and Ron were working together at Oak Ridge National Laboratory, and they were characterizing materials for the use in nuclear applications. And the energy crisis of the 70s happened, and people started using all kinds of natural materials for insulation. And we were insulating homes for the first time, really, in the history of the United States. And at that time, there weren't a lot of standards. There wasn't a lot of best practices in place to make sure that those insulation products were safe. So there were a lot of catastrophic fires that occurred, and the Department of Energy reallocated the group at Oak Ridge to start working on developing standards to make sure that the installation products that are bought and sold in the marketplace are safe, and there's a comparative basis for those products. And so Ron and Dave worked together for a couple of decades before they ever retired from Oak Ridge and started R&D Services. And then my business partner, Stuart Ruiz, and I are the next generation of leadership of R&D. And so that's just a real quick history of R&D. If it has been used as insulation, we've seen it. So you all are, I'm sure, familiar with the common insulation products, but things like hemp, we've seen things like sheep's wool, recycled denim. We've even seen people try to turn trash into insulation products. So we've seen a full gamut of innovative technologies that have come through in the time that I've been here. So obviously, a little bit of background that Ray gave me last night before we got disconnected. You all have had a little bit of conversation about the Federal Trade Commission, some of the pitfalls for builders, manufacturers surrounding R-value claims. And so I see that Gene has posted a document with the FTC R-value rule, and we can certainly talk about that a little bit. One of the things that I actually brought it up, thought that we could share the FTC R-value rule just for a quick overview. So this is 16 CFR Part 460. If you Google R-value rule, this thing is going to come right up. And I'm certainly not going to bore you to death with all of the aspects of this. But the key thing here is this background, products covered. And so specifically, this rule governs insulation sellers when they make an R-value claim in the residential space. And so the question that we get sometimes is, does that mean that if you're in the commercial space that I can claim any R-value that I want? And the answer to that is almost certainly no, because even products that are on the marketplace that are meant for commercial or industrial often find themselves in residential applications, even if they weren't necessarily intended to. And so the FTC really governs all R-value claims, even though that this rule specifically is for the residential market. And then the rule has certain provisions in it. And so anything that home insulation manufacturers, Part B here, professional installers, retailers who sell insulation for do-it-yourself installation, It also applies to laboratories like R&D Services that conduct these R-value tests for those who are going to make the R-value claim. So there are even things here within the rule that we have to abide by as an accredited lab. The rule falls into two basic categories. They talk about mass insulation and reflective insulation. You all fit in the mass insulation category. And the commission is specifically going to be interested in R value claims where the manufacturer has failed to disclose the R value, exaggerated the R value claim, failed to inform consumers about R value's meaning and importance, exaggerated fuel savings and how those savings were calculated, and falsely claiming that consumers' insulation purchases would qualify for tax credits. So there's a very broad application to this rule. And here in the rule requirements, we're going to get into some of the more technical aspects of the rule. So one of the things that we get asked often, we usually measure insulation products at this concept of a mean temperature of 75 degrees. And most of the at 75-degree mean temperature is usually the least amount of time in the year when you actually need insulation. If you think about it, if it's 75 degrees outside, chances are your windows are open, your air conditioning or your heating systems are off. So why in the world do you measure at 75 degrees? And really that comes from the R value rule. They really established the precedent there. It also happens that the equipment that was being used at the time that the rule was developed, 75 degrees was a very easy temperature for them to reach. And so that also was a factor as to why 75 was often used. Really, the key part here is that insulation and the way that we evaluate insulation is in order to put a comparative basis for the uneducated consumer, so that way they can compare thermal performance at common conditions from material to material. And what that means is that just because we measure at 75 degrees, that does not mean that that's the R value in all conditions. So thermal performance changes by temperature. It's directly related to the temperature. And so when it's really cold outside, some insulation products perform worse than they do at 75. And when it's really cold outside, some do better at 75, and the reverse is true when it's very warm conditions. So the thing that we always try to remind our clients is, yes, 75 mean temperature is important, but it is not the end-all be-all of how that product performs over the range of temperatures that it will be used in its application. And so the other, I see that Ray's already asked a couple of questions about the delta T, right? So in the R value rule here, let's see if we can get to the technical details. So they're going to talk, oh, this is the commentary. So the rule specifies a 50-degree delta T plus or minus 10. And most insulation standard specifications that we use, most requests that we get from clients is that we test at a 40-degree delta T, because it's that 50-degree plus or minus 10 that the FTC recommends. Well, why do we test at 40 and not 60? And largely that's because the smaller the delta T, the better the insulation performs. So if we test material at 50-degree delta T or 60-degree delta T, chances you will get different performance, and chances are almost certainly that you're going to get lower performance than you do at 40-degree. So in my opinion, as a practitioner at a test lab, a plus or minus isn't designed to be specified on the bottom end of the plus or minus just to give yourself an advantage. However, the FTC has allowed for the insulation industry to use that 40-degree delta T because it's within their plus or minus. From a laboratory's perspective, when we see a plus or minus, we're really looking at the variability or uncertainty of the equipment. So just because you set a specific delta T in the equipment doesn't mean that you're going to operate within that delta T, that there's some uncertainty there. So that's really important to mention. Let's see.
Now, how would I look at that if I'm a designer, like an architect or an engineer, and I guess more on the engineer side of, I've got these tests. I'm wanting to, because many of us will be builders and will engage engineers, and we need to know what questions to ask them as they're going to stamp plans, based on the results that come back out of the lab.
Right.
Um, is there any engagement that would be useful to unpack right now on that, or is that just something that, what the report says is what the report says?
It's a couple of ways to answer that. One, most of our building code requirements are going to be based on this 75-degree average measurement. So if you have builders that are strictly building to code or to prescriptive requirements as laid out in building codes, then typically you don't get those types of questions. If you start getting into projects where like lead evaluation for energy efficiency, or you're doing like trade-offs where you want to do a little bit higher efficiency component to a structure to gain some energy efficiency, then you start talking about modeling that takes place to determine how that product or technology is going to be used. LEED, for example, specifically has requirements around modeling in a 3-year basis over the duration in that climate zone. And so at that point, you really need to have what I would call a full evaluation over the range of use to make sure that that model is as accurate as possible. And so we always recommend to our clients that while the 75-degree average measurement is required for most standard specifications, it's really their responsibility to have the data available. So where if a design professional is looking for the information to be able to accurately model how that product is going to perform in whatever climate zone they're designing, then they would have that data to be able to give them to increase the accuracy of that model. So unfortunately for the building community and the engineering community, they have to know what questions to ask. They have to find the people at the various companies that they're dealing with that are educated to understand that R value is not just R value, that there is this concept of R value does change according to the temperature that it's subjected to, and that then they have to have that data available to give to them so that way they can make informed requirements. This is especially starting to come to fruition in northern climates. I'm very active in some of the standards development that's going on in Canada, and the National Research Council in Canada is actively looking at how to develop specifically with closed cell foams. Closed cell foams are a whole nother animal that you may or may not be interested in, but they typically age over time, meaning that their R value performance goes down over time. The Federal Trade Commission addresses that rule, but the key part there is in cold climates, the NRC is looking how to evaluate that aging phenomenon at different temperatures other than 75. And we've been involved in some of that activity.
Well,
So
that's good to know as far as like just in the sales conversation when we're talking with people about what they're considering. Because I know the
right,
first time I saw spray foam, I was in my parents' attic in South Texas, and the attic wasn't blazing hot. And I
right,
thought spray foam was the greatest thing since sliced bread. But then, once you learn a little bit more about it in comparison to the environmental impact and the performance of hempcrete, well, then, now it's not so much. And then I think the merit of the fact that hempcrete ages well because it's continually getting better instead of worse. And so that's something that's neat. I had a question that might be a wild sideways question for you. But it just occurred to me, do any of these tests accommodate for moisture or humidity? Because and here's why. One of the big hallmarks about this is its vapor open characteristic, and that moisture can migrate in and out of the material. And so now you've got, Tom up in Vermont, in New England area. You got Tim down in South Texas. You've got Jose in Florida. All different, and then Gene out in Colorado. All different humidities, all different deltas on things. And then, but I know one of the things that contributes to the performance is that migration in and out and the thermal achievements that are there. Is there any test that tests for it or could show it?
Yeah, it was. Yes, but that gets significantly more complicated than just the types of measurements that are required by the FTC. So in the FTC, they actually specify a number of measurements that you can use to satisfy the rule. And C177, C518, C518 here is by far the most common test method that's used. I believe that you all have heard information about C518 in the past, but this is a real key provision here. So this test method covers measurement of steady state thermal transmission through flat slab specimens. So what I wanted to do is take a few minutes and let's see if I can get this shared to you all, and just spend a few minutes talking about the heat flow meter apparatus and how we use that. So what you see on the screen is your garden variety heat flow meter apparatus. Some of you may have seen this before. This particular instrument is made by TA, or it was originally Laser Comp's design. TA purchased Laser Comp. We have 8 different heat flow meters in our lab. This is the 12-inch, 12 by 12 size. We have 24 by 24 inch, and we have a couple 30 by 30s. And we can measure anything from a couple of millimeters thick all the way up to 12 inches thick. So the key part to this measurement it is steady state. So when you start talking about moisture migration through a specimen, at that point, that is not a steady state measurement because you're introducing mass flow and not just heat flow. And so that complicates this measurement because it falls outside of the bounds of C518. So this test was designed for the traditional loose fill air-based insulation products, and we've had to apply it to basically anything that wants to be used as an insulation because of that Rule 460 that we talked about here in a few minutes ago. The concept for the heat flow meter is pretty simple, but complex in application. So the diagram here shows really well that you have a hot plate and a cold plate. So the hot plate's denoted by its red, the cold plate's denoted by its blue, and we can control those temperatures. So in this case, this is what we call heat flow up. So you've got your hot plate on the bottom, the cold plate on the top, and that's going to introduce heat flow from the hot plate to the cold plate. These instruments can be reversed, so we can do heat flow down or up, and we've actually got a couple of systems where we can rotate these and do heat flow horizontal, which is sometimes an interesting thing to look at. The C518 apparatus is what we call a comparative measurement. These plates that are in the center, I should say in the center of each of these plates is what we call a heat flux transducer, which measures a microvoltage. So as the heat flux increases, or as the amount of heat moves through a specimen, that microvolt increases. And then we have to tell that instrument how much heat flux is associated with that microvoltage level. So what we do is we purchase reference material from NIST, the National Institutes of Standard and Technology. They govern commerce in the United States. So they keep all of our weights and measures. Any accredited laboratory has to have all of their measurements traceable back to NIST. So we purchased reference material that we use to calibrate these instruments that allow us then to compare the microvoltage of an unknown sample to the microvoltage of our known NIST traceable material. So this is a comparative measurement. And so that's the basics behind how these instruments work. Again, most tests that we do will have a 40-degree delta T. There's some countries around the world that have slightly different temperatures that they use. But the larger the delta T, the larger the heat flux, and that's going to impact the reported results.
What delta T can you test up to? Like if somebody just wanted to fart around with something and see how it did?
Theoretically, it depends on the calibration of the unit. The way that our 12-inch units, in theory, we could probably do 120-degree delta T. Mm-hmm. Because our instruments are calibrated, I mean, maybe even more than that. It really just depends on the calibration level of the instrument. The downside to that is these plates have a certain limit to how much heat flow they can measure. So the larger the delta T, the higher the heat flow level is going to be, and you could, in theory, saturate the plates, meaning exceed their ability to measure the heat flow. And so that would be the limiting factor. But if you had a really good insulation, like say a vacuum panel that might have like a R60 or R80 per inch, in theory, you could probably run it up to 100, 120-degree delta T and still be able to make some sort of measurement with the instrument.
Yeah, as an industry, as we're getting into, having that comparative scenario side by side, it sure would be fun to, run a bunch of those variable, different deltas and, just crush the competition and then show and tell. So I'll put that on my list of my wish list for Christmas on different lab tests.
Sure.
So, yeah.
Now, one of the things I would tell you is the combinations of temperature are infinite, right? Mm-hmm. You think about just the climate of the United States between the hot, humid climate of southern Florida and the cold, arid of northern Alaska. The potential temperatures that you could test are infinite. Well, none of us have infinite budgets, so how do we accomplish covering the full temperature range? And C518 is literally just what you see on the screen. That standard just describes the instrument and how to make a valid measurement with that instrument. The calculations of all of these different measurement standards have been pulled out into a practice named C1045. So ASTM C1045 is the practice that governs the calculations that we do to determine thermal performance. And the reason why they did that is because C177, C518, C1114, C1363, C335, like all of the different measurement standards that we use essentially had the same calculations. So instead of repeating those calculations 10 or 12 times, they pulled them out and put it into their own practice that could be referenced by all the different measurement standards. What that practice allows us to do is we could measure anywhere from 4 to 9 or 10 different temperatures across the range of use. And then we can put all of that data into a regression analysis that will give us a curve that we could then calculate thermal performance at any temperature range over that measurement range. So that turns normally we do anywhere from 9 to 10 measurements when we're doing that. So we'll start really cold and work all the way up to really hot. And we can turn your 9 or 10 measurements into infinite R values on different hot and cold temperatures over that range of measurements. And so that's really what you would be interested in, Ray, is to do a limited number of measurements, a little bit of calculation, and then you have your infinite number of R values that you could claim.
Sounds like we just need to show up with a case of beer on Friday and some lab samples, and then have some fun.
Sure.
But I don't want to get us too side railed on things, and just to get us back on track. Now, this is something that I know Cameron has done as a supplier,
Yep.
And then I know as I have been advised to look at doing this as a builder or general contractor, subcontractor, which seems an odd thing to do, but especially if I'm going to either make that claim, I either want to do it or to validate something, and then just have it as a show and tell. So walk us through that process if this is the time to have that conversation. If not, you can table that for later about how we would go about that.
So the traditional way of making those claims, if you're a builder, is you're purchasing whoever the manufacturer is of the insulation technology usually supplies the data for the claim. So you show up at Lowe's or Home Depot or Menards, depending where you're at. You walk to the shelf and you see an R15 or an R21. You pick up that bag, and the supplier is responsible for that claim. In that case, Lowe's and Home Depot, or whoever your supplier is technically responsible for that claim. They are relying on the manufacturer to provide the validity of that claim, right? So they basically just pass that back to the manufacturer. Spray foam companies are interesting because the spray foam companies often supply the part A and part B, and then that is manufactured on site, which is very similar to your industry and the things that you all are working on. And so in that case, the spray foam company does a lot of work on spraying samples and making sure that they meet the requirements of how to spray those samples. And then if you spray the samples per their instructions, this is the R value that you could expect, right? And that's some of what I think that has gone on, is that the suppliers of your materials have done some testing and say, okay, if you apply the material in our per our instructions, then you would expect these R values. If you have no data and you are making an R value claim, then you would be responsible to have some sort of sample or some sort of data to back up that claim. And the FTC R value rule says that you have to maintain test data for 3 years after you make the claim. So if I make the claim today, that I need to maintain the paperwork for 3 years for today's claim. And every time that you make that claim, that 3-year counter starts over. Now, that doesn't mean you need to do a test every day, but it does mean that your test data can't be older than 3 years if you're making an R value claim. So, kind of keep that in mind. Kathy's question about how often we calibrate these. We calibrate them once, but we check the calibration at least monthly. And so as we put that same reference material back in the instruments, we run it as if it were an unknown. Then we compare that measured thermal conductivity or thermal or R value to the value that NIST gave us for that piece. And typically it's less than 0.5% different, which tells us that the calibration is still accurate and valid. These instruments are very expensive. Instrument that you see there on the screen starts at $40,000 or so, and they go, the bigger they get, the more expensive. And so the 30 by 30s are upwards of $140,000. Lab samples cost can be anywhere. Okay, so specific to your materials. Okay, so we would need those materials to be dry, and by dry I mean steady state. So we would not want them losing mass as the moisture in the sample equilibrates in the lab, right? So once they reach steady state, then we would put these things in the heat flow meter and let them run. These things often take a long time to run because they tend to have a very high density. And so normal tests will take 2 to 3 hours to run for a single set point. I would not be surprised if these tests take longer. I think that we've done some tests in excess of 24 hours on this material just to make sure that it really did reach steady state. That said, the FTC talks about characteristic thickness. So the characteristic thickness is the thickness of the material that once you get beyond that thickness, the R per inch does not change. Okay, so I said a lot of words there. And what does that mean? We talk about thermal performance in terms of R value. So 3 inches of such and such insulation delivers X R value. And then we also talk about thermal resistance in terms of R per inch, which we call thermal resistivity. So if you take that R value and divide it by 3, because it's 3 inches thick, you would get an R per inch of X divided by 3. Okay. And this was something that when I worked with Cameron on that sample preparation standard that they were working on through the ASTM D37, one of the things that I tried to explain to them is that once you figure out what your characteristic thickness is, that really helps you because you don't want to have to make an R value measurement for every single thickness that you could possibly install. You don't want to have to measure 8 inches. You don't want to have to measure 12 inches. You want to figure out what your characteristic thickness is. So that way, if it's 3 inches, then you can get that R per inch and multiply it times whatever thickness you're installing and know what that R value is. This is very common if you go to the hardware store and you test loose fill materials, you will see a coverage chart on that bag that'll tell you how many bags per 1,000 feet you need to install for a certain R value. They establish that based on that characteristic thickness. They are not measuring all of those different thicknesses. They're usually for loose fill materials, it's at least 4 inches thick. 4 to 6 inches thick is pretty well known to be the characteristic thickness for that material. So those are some things to think about, Ray, because that is kind of important. My assumption, and when I worked with Jacob Waddle and Cameron McIntosh, one of the things I told them is my guess is that this material's characteristic thickness is going to be quite a bit thinner than 4 to 6 inches thick. So that. Hopefully that answers your question, Klaus. I don't know that we've tested silkworm cocoon insulation. That would be an interesting. That would be a very interesting sample that I would like to see. And then diminishing return. Are you talking about the amount of R value that you get before you start to?
Right. And then I've heard that conversation that, such and such thickness, and everybody comes back to that. Well, it's about, R2 per inch, however many disclaimers you want to put in there. But that's what people are kind of settling on. And then with the monolithic characteristics of it and the other advantages, it performs much nicer than that on a day-to-day use. But then if you've got that R2 per inch anecdotal number, and then, is a 30-inch wall going to get you, that much of a benefit? And then I have heard, narratives that, once you get past 10, 12 inches, that's kind of a diminishing return on the benefit that you get insulative or otherwise.
Yeah, so a good way to think about this is if we had a glass window that the sun was shining through, and we took paint and we rolled one layer of paint on that glass window, the amount of light that would be restricted pre-paint, post-paint is going to be pretty significant with that one layer. Now, if we add a second layer of paint, it's going to further reduce the light that goes through the window, but the percent reduction from layer 1 to layer 2 to the overall amount of light that came through that window is going to be significantly less than just that first layer, right? And so this third layer, again, is going to be a much smaller reduction than the first layer. And so insulation is the exact same way. And most of the folks that are in our community, if they're really being honest, they've gotten to the point where they recognize that the building code and the energy codes around the United States have pretty much gotten to the point to where they have reached the diminishing returns. The R value that's required in walls and ceilings and homes has pretty well got to the point to where the insulation manufacturers are just making a little bit more money, and that the homeowners, to go from R30 to R35 or R35 to R40, the amount of time that it's going to take for that to pay off is usually exceeds the average time that people own their homes. So at that point, they've lost money because that's not the way that homes are priced. So that's probably where you're getting to that point. The hard part, and I've had lots of conversations from folks in the industry with these high density mass insulation, is how do you account for the thermal benefit that you get from having such a thermal mass that you're using.
Right.
And that is a very valid question. It's also one that's very difficult to answer. And in a lot of ways, your material and your products are very similar to what we call phase change materials. What phase change materials do is they act as like an energy storage tank that delays the energy transfer to the building to lower the peak demand, right? And that is where your products or these products really benefit, is to delay that peak energy transfer, and even to stop some of the energy transfer, because say when the sun goes down and it cools down outside, you start to reject heat back to the outside instead of it going through to the conditioned space. And there are ways to do that. They're not cheap. They're very expensive. Oak Ridge has what's called a climate simulator, and that climate simulator basically simulates an attic, and they can run it through a full range of conditions, and it's quite an expensive test. So a couple of, Tim, you bring up a really good question about the ASTM test for PCM. So I can't remember the number right off the top of my head, but there is a test method that we use using the C518 apparatus in what's called dynamic mode. And what we're using the heat flow meter to do is we're changing the temperatures on the plate in a dynamic fashion. We're not letting the instrument get to steady state. We're changing the temperatures of the plate and measuring the sample's response to those changing temperatures. And it allows us to get specific heat. It allows us to quantify how much the material delays the peak load. It is a very difficult test. It takes a long time. There's a lot of data analysis to it. You have to have the special software purchased from the manufacturer just to be able to run it. But that would be a test that would be interesting to see what this material looks like compared to a PCM, because I think that this product embodies a lot of what people are trying to figure out how to use PCMs in the marketplace. As far as changing the humidity inside the chamber, no, you don't. Mostly because the cold plate typically is below the dew point in the lab, and if you aren't careful, you'll get condensation on the cold plate, which will cause the measurement to be quite inaccurate. You're starting to introduce mass flow to that cold plate, and you can actually damage the instrument if it gets too wet. And so usually this is done at constant humidity in the laboratory conditions, so that way you're just looking at thermal performance. Now, there are things that we can do to evaluate how this product would behave in various humidity environments. Have you all ever heard of Woofy, which is a software program for hygrothermal modeling of building assemblies?
I haven't.
Okay, so Woofy is a software program that um, allows us to input physical properties of assemblies, take outdoor climate files, and model, let's say, a wall assembly with rain, sunlight, changing temperatures. We can change temperatures on the inside of the building, and we can literally model how well a assembly does in various climate zones, various locations, various assemblies. There are 5 key properties that you need to know about each of the materials. So thermal performance, thermal conductivity. You need to know about density. You have to know about specific heat, porosity, and water vapor transmission rate. So if you have those 5 key properties, then you can at least start. There are a number of properties that you need to have. So that's going to get you what I would call like the base model. There are some temperature dependent properties that if you had some additional data, it would improve the accuracy of that model. And so Woofy is something that would, I think, answers at least some of your hypothesis about how this product performs in various humidities and things to consider. And Tim's point about PCM materials not letting condensation, part of the reason that PCM materials don't allow condensation is because they're often encapsulated in vapor impermeable barriers. So think about ketchup packets and think about a blanket of ketchup packets. That's often what PCM materials look like. So the media in the packet is the PCM, and it has a freeze thaw temperature that is going to be based on what PCM you use. So maybe it's 82 degrees is when the PCM starts to melt. And then once the wall gets below 82 degrees, it starts to freeze again. So that's the reason why PCMs don't allow condensation to develop, is because they're often encapsulated in that vapor impermeable jacketing.
I think that it's a good thing to break down this into 2 approaches. The first approach is to simply play the game by the current rules.
Right.
And then those are the hula hoops that are in front of us. And then we can play our game, and then we can flex muscles and really show and tell and be comparatively excellent. And I think that's the more expensive long-term industry building thing. And I know that's there's grant monies being sought for that from the environmental stewardship approach to building science, and so a lot more of that is to come. And so just to cover the bases is where we are first, and to make sure that we are playing the game by the rules, so that we don't show up, be excellent, and then get our teeth kicked in because we didn't follow a rule and didn't jump through a hula hoop that we really didn't need to, but it was part of the game. And so
I would agree with that. I think one, it's required by law, so I mean, I just, that's just kind of, you can't get past that. If you're making an R value claim, it's required by law. The other part, some of the big industry associations that are out there spend a lot of money to protect their own interests. And as you start to get market penetration, and as this starts to become more and more widely accepted, you're going to start getting market share from some of these very big industries who have staff attorneys that like to write letters and to ask for validation of your claims, or so I'm almost, I'd say probably 5 or 6 times a year, I'm aware of somebody that we work with who receives a letter from one of these big manufacturers associations. So they police the market and do a lot of work to make sure that they're protecting their market share. So it's just in your best interest that as you start to get market penetration, that you cover your bases and protect yourself. I think that that's wise.